So this is gonna be Zichao's last discriminant seminar talk before he leaves, I guess.
I still have 1 month-ish.
Yeah, but still, we don't have any more time slot for speakers. Yes. We talk about odd even towns, right?
Yeah.
Please.
All right, so thank you very much for the invitation, and today I'm going to discuss something from the last summer. This is a Apple Pro summer research program suggested by Lan Wei from Shandong University, and finally we successfully worked it out with Minghui Ouyang from Peking University, who is soon joining Zhejiang University as a postdoctoral researcher. This comic shows that we have a bunch of clubs in a town, and keep in mind that in every town we have n many people and n many distinct clubs. So meaning that I do not allow two clubs sharing exactly the same list of people. That doesn't make sense. All right, so still I should make a brief review on what odd towns and even towns mean. Actually, this was already reviewed by Ting Wei from 2 weeks ago, but probably if people are not working on these kind of problems, it's still something to mention. So already from the definition of odd town, it shows that we cannot allow two clubs sharing the same list of people, because otherwise, if we just take the intersection of the same clubs, then it's not possible. So in an odd town, we have odd clubs with even intersection sizes, but in an even town, we have even clubs with even intersection sizes. So this is kind of confusing for the very first time, but soon you will see some reason on why they're supposed to be very different. Alright, let's fix some notations. So we have this bracket n, or 1 through n. We have this power set 2 to the n as all subsets of n. I always think about my set family, well, and like the collection of all clubs that can be viewed as a set family. And so Fi is the club, and F1 through Fm are the collection of all clubs. So if I want to think about these as people, and this is the collection of all possible clubs. And here, this is the actual M clubs. this language, what is an oddtown? An oddtown is every set is odd. Every intersection is even. Well, what is an eventown? This is that every set is even. And every distinct pairwise intersection is even again. So maybe I should include some example. So here we might have 1, 2, 3, 4, 5. And here I can have 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So it is easily seen that here every club has odd size, while every pairwise intersection is empty and so obviously even. And here every set is like 2, 2, 6, and the pairwise intersections are like 0, 2, 2, they're all even. So as a famous historical problem, these has answers, so sharp answers due to Burlingame and Grave. Of course, as usual, as usual two-round problems or as usual extremal set theory problems, we care about the maximum size of the maximum number of clubs, because you can always have no clubs which vacuously satisfy all the restrictions. But definitely we want the maximum. So the theorem says that if we have an odd town, then we have at most n clubs. And the construction is the kind of stupid one. So we just put together all the singletons, and this is obviously an odd town. But the upper bound is kind of more interesting, and this might probably be the, I'm not sure whether it's the first in the history, but it's probably the first one where people study the so-called linear algebraic methods in extremal combinatorics. And so the point is to see that all the indicator vectors are linearly independent. And why is this so? So, well, first maybe let me explain what is an indicator vector. So like in
here the field is F2.
You can work in F2 or you can also work in Q or Z. I think they both tell you the same thing. So if I have 1, 3, 4 in my ground set 5, then the indicator vector is one, 0, 1, 1, 0. Because this first one is indicating 1, and they are indicating 1, 2, 3, 4, 5 in this order, and so we have 1, 3, 4. We have this vector. And why do they linearly independent? So because if we have then I just take the inner product of both sides with an arbitrary bi. It shows that so because bi inner product bj is 0. Yes, because this is an odd town, and so all pairwise intersections are even. So the only thing we are left is that exactly that bi inner product bi, which is 1. So we have ci is equal to 0. But this is the definition of being linearly independent. And since we are working on the f2 to the k, it just follows that the number of clubs, this m, is upper bounded by m. And the story for this eventown might be slightly more complicated. I think they are independently discovered by this per attempt, and great. Who showed that eventown implies that m is upper bounded by 2 to the n over 2. And this might be a bit scary at the first moment, but it's actually quite natural. And the construction is that, so just motivated by this example, we basically take all possible combinations of 2 sets. And because we have n over 2 many packages, like 1, 2, 3, 4, all the way until n, we have n over 2 many packages, and for each package we either choose it or not choose it. So the number of sets is 2 to the n over 2. And the upper bound is still some linear algebra, but it might be slightly more advanced than that one. So instead of looking at these indicator vectors, we need to look at their span. And the crucial observation is that this span is a self or orthogonal linear subspace. Because for every fi and fj, no matter whether I and j are the same or not, the definition of eventown shows that their inner product is always 0. But then you can run the rank nullity estimate to show that this space cannot be larger than half of the whole space. And so the dimension is upper bounded by n over 2, meaning that the number of sets in this dimension, the number of clubs upper bounded by 2 to the n over 2. All right. So this is the history review, and now we need to dive into the problem we are going to look at today, which is called alphatown. So what is an alphatown? We first consider a 0, 1 vector of length k in in f2 to the k. And we call the collection of clubs, this curled f, as an alpha town. Every I-wise intersection is equal to alpha I mod 2. And of course, I need distinct here. So in this language, it is easily seen that our odd town is a 1-0 town, and our even town is a 0-0 town. And so this motivates us to define the extremal function f alpha of n, which is the maximum of f, where f is an alpha town on n. And so with this definition in mind, what we have already seen, the results due to Berlekamp and Grave, are that f10 of n is n, and f00 of n is 2 to the n over 2. And for people who are interested in playing with these vectors, so an exercise you might want to try it by yourself is that this f01n is n for n minus 1, while this 11n is 2 to the n minus 1 over 2. So they basically have the same answer, which indicates that it is not very interesting to look at this 0, 1, 1, 1, because actually their structure are majorly already captured by this 1, 0 and 0, 0. But still, if you want to work out the precise answer, then it takes some work, and so it's an interesting exercise. You might want to try it by yourself.
So what do you mean by n or n minus 1? Does you mean
It
depending
means
on n? Or?
Depending on the parity of n.
Oh, okay.
And actually, the study of these problems was initiated by Johnston-O'Neill. In 2023, and what they did is basically they figured out this f alpha of n for every alpha of length either 3 or 4. And later, their results were partially improved by Wei-Xin here, in the sense that they proved this f alpha of n is basically this one times for subspecial alpha, but it's not that special in the sense that this alpha So of course, people may ask what this t is, and this t is that the vector alpha looks like I have a bunch of something that I don't care, but then suddenly I see the very last one in my vector, in my 0, 1 vector, and then after this final one, I have a bunch of zeros, but then the point is that this final one appears at the tth bit. And this t, and the first half is shorter, and the second half of zeros is longer. And if your vector alpha looks like this, then they claim that the answer is t factorial times n to the 1 over t.
So by long, you mean at least t?
Yeah, at least t. I can sketch the proof for this. Actually, this is not very hard. So, but it's quite important for our result. So the point is that I consider this I consider the collection of all possible t-wise intersections among my f. And then this guy is actually an oddtown. And why is this? Because my alpha is, because the tth bit of my alpha is 1, and so everything in itself is an alpha thing. It's an odd cloud. While what happens later is that if I take the intersection of some t-wise intersection and another t-wise intersection, then I'm taking the intersection of at least t plus 1 many members from my original town, which shows that that one has to be 0. That one has to be even. But then how many members do I see here? This is exactly m choose t. Well, at the first glance, this is not obvious that this is exactly this many members, because you might want to you might argue that maybe the intersection from A1 through AT and the intersection from B1 through BT, they are the same. But it's not possible, because otherwise you will contradict this sharp transition from 1 to 0. And so this guy is upper bounded by the oddtown theorem. This one is upper bounded by n, which solves to m is upper bounded by t factorial times n to the 1 over t times some lower order term. Any questions so far?
How do you do the robot? Because you know this f alpha n is equal to the this defect.
Do you have a matching lower bound?
Yeah.
How the robot?
So you will see later. Okay. Actually, the second half is more on the explaining why do we expect this kind of lower bounds. Our result is, in some sense, complete solution to these problems, where we show that this f alpha of n is 2 to the n over 2 if alpha is 0, 0, 0. And maybe let me rewrite it in a more confusing way.
What's LV?
Level. Yes, and obviously the questions are what I mean by level and what I mean by grade. And actually the second half of my talk is devoted to kind of motivate these definitions. So I'm not going to define immediately for you, but hopefully you will see the motivation behind defining these things and to prove the full theorem. This is the plan. Yeah, because actually, if I can write down the definition at this moment, but then it doesn't make sense.
So grade is always 1 or 2?
Right. So it's, in some sense, I need to have a linear decomposition of alpha into some prescribed vectors, and the linear expansion or linear decomposition in that basis determines the level and the grade, and that will give you the complete characterization of this f of alpha. But to start with, I need to I need to gradually answer Hyungwoo's question, like, what are the constructions like? So, the first thing to look at is this f of 110n. And this was proved in the exact form by Johnston-O'Neill that this guy is, I think it's either this n over 2 or this n over 2 minus 1. But I just write plus minus 1. I don't care about the exact form. And so how do I see this? And the construction is we somehow put together two different oddtowns. So do people agree that this 1, 2, 3, 5, 4, 5 singletons, they form a maximum oddtown on 5? But also, I can have a different oddtown. Maybe let me write tilde, because this is not the traditional 0, 1 oddtown. This is a 1, 0 oddtown. No, this is a 0. Sorry, this is a 1, 0 town. So by oddtown I mean with 0. Wait. So by oddtown this is 1, 0, and this is 0, 1, and eventown is 0, 0. So let's carefully check their intersection pattern. Up to 3 wise intersections, because I'm looking at 1, 1, 0 in F2 to the 3. So every singleton is definitely of size 1, and then every pairwise intersection is already an empty set, so this is 0. But also every 3 wise intersection is obviously another empty set, so this is 0. And for the second line, then this is more interesting, because every singleton is a 4. And then every pairwise intersection is 3. So this is 1. And then every 3-wise intersection is of size 2. So this is another 0. So what is my 1, 1, 0? My 1, 1, 0 is the summation of 1, 0, 0 and 0, 1, 0. And so this will motivate a kind of interesting construction which is that I have a 0 here and here. And from the first half, I just delete everything except that I want to keep the exact I. Well, at the second half, I just claim everything except that I delete this n/2 plus I. And so you can easily verify that this configuration,
So sorry, what's the definition for the first part?
I just take I and throw away everything else.
Singleton.
Oh, a singleton. Okay.
A singleton. And for the second half, I just delete this. So basically, it's the complement of the first half, but I just shift it. And
But is n even or
sorry.
is n even or?
Yeah, you need certain parity constraints on n to achieve this. But for an arbitrary n, you can just say I throw away the last thing, and I'm working on n minus 1 or maybe even n minus 2 something like this, and I can throw away a negligible part to reduce the configuration to something like this.
Like so I become that plus and minus 1.
So I think the full solution depends on n mod 4. But I don't go into that level of details because I think in order to prove this, you need to kind of forget about that level of details. You need to basically focus on the underlying structure like this to understand what's really happening. And so this will tell you that f of 110 of n is bigger than or equal to n over 2. So from here you can basically see something like why I should expect divided by 2 here. Like if I put in t equals 1, then this is exactly the lower bound here. Although I didn't explain the upper bound for this one, I will not explain the upper bound for why do I have this n over 2, but it's kind of not very difficult to imagine that basically you kind of do this, say f intersecting a and f intersecting the complement of a, you just somewhat introduce a double cover of the original family and to show that the double cover is an oddtown, and that's it. But still, this is not very satisfying because Helm was wondering why I have this teeth root. Well, this is still something linear. So I need to review a second result due to Johnston-O'Neill, where they worked out this 0, 1, 0, 0. And because now the answer is square root of 2n, meaning that you cannot expect some careful, like I just somewhat design my interval to put together things. It's not going to be giving you this, so I need something different. And I think that's exactly the point where this problem started to attract me to think about it. And let me show you an example where n equals to 10. So now my ground set is the complete graph K5. And my class,
this vertex set or edge set?
edge set.
Edge set, okay.
And my clubs are stars. So let me spend some time drawing. Maybe I should have drawn this beforehand, but anyways, I forgot it. at the red intersection pattern. So if I take every singleton, then I have 4 edges because I'm drawing these stars. So I have 4 edges. And if I take the pairwise intersection, so then exactly they are sharing the, if I take 2 stars, then they are sharing the edge joining the centers of these stars. So I have exactly 1 edge. And then everything else is 0. So this is 0, 1, 0, 0. Okay, great. So this is what I'm looking for here. And so what I want is that I want my n to be L choose 2, which will give me a 0, 1, 0, 0 town of size L. And if I put things together, I will see that my m is basically lower bounded by square root of 2m.
So you want L to be odd, right?
To be square root of 2m. Yeah, you are right. I also need some pairwise, some parity restrictions on
Yeah.
L, but
Otherwise, it's going to be 1, 1, 0, 0.
yeah, but that's still something covered by here. Yes, and I believe that Hyung would also agree that I can somewhat tweak this construction to prove Xin Wei's result, right?
Yeah,
I'm instead of looking at these graphs and stars, I'm looking at hypergraphs. Yes. But then I think this is basically the new thing in our work than the previous works, because basically I would say that our work is kind of we just put things together from previous works. But unfortunately the previous authors somewhat neglected some interesting stuff, and so they turn to prove some weaker characterizations of this f of alpha, but instead I kind of believe that it's possible to determine this f of alpha exactly, and so luckily I was spending more time on these constructions to finally motivated my own definition of these levels and grades. And this is still inspired by the previous operation, by taking the complement. So now I'm looking at the complement of these stars. And they are also highly understandable. So what they are, well, first, for every one itself, it has 6 edges. 4 choose 2, which is 6 edges. And for every pairwise intersection, they intersect at 3 click. So this is 3 choose 2, which is 3. And for every 3-wise intersection, they have a common edge. So this is 2 choose 2. And this is 1. And finally, if you want to think, you might think about 1 choose 2, but definitely this is 0. And this one reduces to 0, 1, 0, 1, 0. All right. But this is kind of, the point is to kind of think that, okay, these are different things. Like these are, I don't know in what sense, but in some sense different. Just as before, I can put together this 1, 0, 0 and this 0, 1, 0 to obtain something like a division by 2. All right. So maybe let's briefly summarize what we have seen so far. So we have seen 2 ideas. The first one is that to solve this 1, 1, 0 problem, we are playing the jigsaw puzzle by putting two different constructions together to lose a factor of 2. And the second one is that I was looking at this 0, 1, 0, 0, but then this has some essentially interesting construction, which are these stars and typograms. All right. And the idea is to play everything together as a big jigsaw puzzle instead of so here I'm just playing a jigsaw puzzle with 2 pieces, but I want to play a jigsaw puzzle with many pieces. So now let me introduce the crucial lemma, which is also called Cartesian sum. So this is basically an abstract way to say that what I was doing here. Like I have a alpha town and I have a beta town. And I want to somehow put this alpha town and this beta town together to get an alpha plus beta town. But then I will unfortunately have to lose something on the ground set, because I want disjoint unions. So I need to have this x plus 1 lost here. And the proof is also quite simple. I just construct an alpha town achieving this f of alpha x. And I also somehow achieve this f beta of y. these are the weaknesses. And these are also on the ground set X and ground set Y. But now I want to draw a larger thing, which is X plus Y. And I put AI here, I put BI here, I take the union. So it follows that this dot implies that I'm shifting and then taking the disjoint union. But then I also need to somehow answer the question, right? I call it crucial. So why crucial? Well, actually, I will use that lemma in two different ways. The first way is just what we have already seen, which is the jigsaw puzzle part. So if I already have large alpha I towns, then I can play this jigsaw puzzle to combine these towns into a large alpha 1 plus all the way through alpha t town. And this is exactly the way I will put together all my singletons, all my singleton complements, all my stars, all my star complements together to get the lower bounds in my main theorem. But then there is a kind of secret second way, which first you want to see that this is a strong triangle inequality. But this terminology from kind of functional analysis is not that important. The important thing is that we can apply this fact reversely and to contribute to the upper bounds. And why should I expect these? The thing is that if I have an arbitrary alpha, but then this alpha is arbitrary, well, I want, can I still find it? No, but I actually like Wei-Zhang's alpha, not an arbitrary alpha, because an arbitrary alpha is not something I understand. So I need to take a linear decomposition into this alpha star plus some data, right? And here, my alpha star is a Wei-Zhang-Ge vector, like this star, 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 and then 1, and then many zeros. And then I need to say something about my beta. But then what I want to show is that this beta has smaller level, meaning that the resulting town is much larger than this one. And so I can, to make things balance, I can choose a small y and a big X. And so the whole thing is basically dominated by X. So what I want to say is that up to the contribution to the upper bound, this term is negligible. Yeah, this is the high-level idea behind the proof, which I'm not going to go into further details. I think I'm kind of running out of time, so let me briefly explain what you should do after all these observations. Basically, what you want to do is that you want to somewhat collect all these binomial coefficients and then make them a big infinite matrix, and showing that no matter what minor I'm looking at, I will see a square matrix of full rank. And so because I'm having an infinite matrix here, and I need to argue that all these principal minors, they are of full rank, meaning that if I take the k by k minor, then for every alpha, I can just decompose my alpha into these so-called canonical vectors. And I name my first canonical vector as of level 1, and then the first one is of level 0, and then 2 vectors of level 1, and then 2 vectors of level 2. So why do I name it in this way? Because my level 0 canonical vector is just the eventown thing. So it has to be this 1, 1, 1, 1, 1. And then my 2 vectors of level 1, they are the singletons and the n-1, so complements of singletons. So it has to be 2 vectors of level 1. They contribute to the linear terms. And then these pair of stars and star complements, they contribute to the square root term, and later cube root term, and then fourth root term, all the way until this tth root term. Yes, and then it's a kind of not very difficult, but I would not say they are trivial, like some matrix operations to argue that all these principal minors, they are linearly independent, and so everything works out and gives you the correct result you are looking for. But I think these parts are, this part is slightly technical, but I would say that the more interesting part of this research project is to realize all of these underlying structures, not to work out or verify all the details actually work out. That's something basically you expect to be true, and also you do the standard thing and they turn out to be true. Okay, so that's it for my talk.
Thank you. Any questions?
Do you know the little O1?
No, it would be messy. I would say it's probably very messy.
Can you generalize to modular P versions? There are many intersection theorems, right?
Yeah, I think that should be the next step. I mentioned this kind of generalizations in the concluding remarks, and for people who are interested, you can try working. I think you definitely will need some, as long as you are not working on this parities, you will need some new technologies. Yeah, but still, that's very much worth exploring afterwards.
Do you know whether Johnston-O'Neill's region has been studied for modular 3 or?
They had some partial results on modular 3, but then they still have some open problems to be answered.
Can you say something more about moving oddtown? Just mentioned from protein.
So I have an arbitrary vector here, right?
Yes.
And I assume that this vector is of level t. And then I need to look at your vector. Maybe I cannot remember all the details, but maybe a carefully chosen vector of your form, which is also in the level t, such that the difference between my original alpha and this alpha star is some vector of level at most t minus 1. And so this one will then dominating in the sense of construction, and hence negligible in the sense of the partition sum lemma. I mean, for this step, you need to think more carefully because it's kind of confusing at the first moment. But if you actually write down everything and then you check it carefully, you will see what you want. Or if you don't want to think about it for yourself, you can read our paper. Right? Mm-hmm. It's slightly technical, but it's not something crazy.
So what you mean is that if you have something bigger than the bound for alpha,
Yes.
then you combine with the beta, then you get something too big for alpha star, right? And then that's contradiction.
Right.
Okay.
Yeah, this is the magical part of the strong triangle inequality.
Any other questions?
Does it make sense to think about cross intersecting? So you have now like different families and maybe like some interactions between some of the members of the first and the second family.
I guess you can also, I guess there's also some future directions to explore, but currently I haven't seen work on that direction. Like meaning that you have, say, 3 families, you are looking at the 3 Y's intersections. But it sounds interesting. I don't see like previous work on that.
No, it's okay. I'm thinking.
If there's no further questions, let's thank the speaker again.